Welcome back. Today we are discussing epidemiology. As usual, here are your student learning outcomes with the corresponding section in your textbook. Hope you're doing all right today. So we're going to begin our discussion talking about a man we've already discussed before, Ignaz Semmelweis. And we know that he's the father of aseptic technique, but he was also sort of an early epidemiologist before the science was ever even created. So he was a Hungarian doctor. He was working in Vienna at the time, and he observed that women that were being tended to by medical students had 4 times likely occurrence of what was called childbed fever. The other name for that is puerperal fever. And so they would deliver, but then they would die after delivery from an infection. And so he realized that the women that were being tended to by midwives had a higher likelihood of living. He also made an observation that he had a friend that sustained a scalpel wound injury during an autopsy, died of similar symptoms to that puerperal fever. And so he kind of reasoned that maybe there's some sort of poison that killed his friend, could also be transferred to women in childbirth by those medical students. Now, this was really revolutionary because at the time this was before the germ theory of disease. So there's still all that, thing about spontaneous generation and miasma. It was all just bad air that was doing it. So he decided to test his hypothesis. He had the medical students wash their hands with strong disinfectant before going to the maternity ward. And the results that he found was the incidence of that puerperal fever dropped to 1/3 their previous level. So this is one of the reasons why hand washing is such a big thing, but also just the fact that he made these observations. He even came up with a hypothesis and he tested this, really drew a very big life-saving conclusion. I never knew it happened to Ignaz. My poor heart is just breaking for him. If you read your textbook, you'll find out that he was not very well received because people did not want to believe that it was their fault that all these women died. And once again, this was before germ theory, so he was under a lot of attack for his ideas on hand washing and how this prevented disease. So much to the point where he went back to Hungary. He actually had a nervous breakdown. He was committed and he died like days later after being committed. Allegedly, he was beaten by guards and then died of infection. Isn't that just a rotten ending for a man that came up with hand washing and aseptic techniques? Okay, so we've defined this before, and actually some of these slides you've seen earlier, we're just going to kind of go into a little more detail. So epidemiology is the study of distribution, cause of disease, and population. And oh, they've gotten so much attention as of late. But what they do is they collect data, they compile it about the sources of disease, risk factors. They are the ones designing the strategies to prevent, predict spread of disease. And really, they do take into consideration and draw from a lot of different disciplines. So ecology, microbiology, sociology, statistics, psychology. And a lot of our daily habits like hand washing, social distancing, how we dispose of medical waste are all going to be based on epidemiology. So those are some basic concepts. So diseases, we've looked at this before, but just it's kind of a nice review this chapter. We'll be bringing up a lot of our friends that we looked at earlier in the semester, so meaning the bacterial diseases, protist diseases, helminths, fungi, all of those fun things are going to come back up just a little bit, just in time for our final. So awesome. So communicable contagious diseases, and we know what that means. They're transmitted from one host to another, either by touch or indirectly by vectors or fomites. And so examples, most of them. Most of those bacterial diseases we looked at are viral diseases. So respiratory infections, sexually transmitted infections, any sort of those gastrointestinal infections by the fecal-oral route. There were some non-communicable diseases that we looked at, and that just means they do not spread from host to host. And so these can be caused like from normal microbiota, being in the wrong place. So, you're not going to catch a UTI from somebody. There's other things where they're vector-borne or if they're from the environment. So examples, you cannot get anthrax from someone else. You're either going to get it inhalation or cutaneously or ingesting Bacillus anthracis or the spores. Lyme disease you get from ticks, so you're not going to catch that from somebody. Cyclosporiasis, usually that's going to be from contaminated water or food. things that are soil-borne, so tetanus, all the clostridiums, most fungal infections, things like that. So there are some things that you don't get from other people. And so those are the non-communicable diseases. Okay, so let's just look at some basic concepts of epidemiology. We're always going to be more concerned with rates per populace than overall number. And so I just kind of grabbed these off the internet, and I did this on the April 29th. So looking at COVID-19. If you just look at numbers, you would say, oh, okay, well, the United States has the most cases, like, oh, you know, we're all sickly. But that's really not the case. So if you look over here, this is going to be total number of cases per 1 million people, so population. Once again, this number, you can kind of do your statistics any way you want to. You can do them by 1 million, you could do it, usually it's going to be by 100,000 people, it could be 10,000 people, it just kind of depends. Since we are getting our numbers daily basically, and we are, as I'm recording this, in the process of a pandemic, it's going to be per 1 million, because nobody wants to talk about, you know, 0.4 people. And so, yeah, so then if you look at it per populace, you see at the moment, you know, Spain has more cases per populace. Two, if you look at total number of tests, you can say, oh, well, we're testing, you know, way more people, so therefore we're doing more testing, but that really isn't true. So you got to pop over here to how many tests per 1 million of our populace. And so we're not doing the most testing. And from this list, you can see, oh, Germany has tested more of their population. So a higher percentage of their population. So you always want to look at all of these numbers and look at it as a rate per populace. So another rate. So the attack rate is the proportion of susceptible persons developing an illness in a population exposed to an infectious agent. And so here's my example because it's nice and it's easy. So let's say we got 100 people at a party, and these 100 people eat the chicken salad, and 10 of those people get sick. And so yes, I kept the math very easy. So this particular disease would have to have a 10% attack rate. And so it's just, it has to be susceptible person. So since we were talking about a little outbreak at a party, if they didn't eat the chicken salad, then they wouldn't have gotten it. So things that are going to be reflected in that attack rate are the infectious dose. And remember, we talked about this a long time ago. An ID 50 is the dosage required to make 50% of the people sick. So if something has a lower infectious dose, meaning it takes few of those microbes to make somebody sick, that means that particular disease is going to have a higher attack rate. If it has a higher infectious dose, meaning it takes more microbes to make somebody sick, that it's going to have a lower attack rate. It also is going to depend upon the immune status of a population, because it could be, we're talking about particular populations. So if this party happened, you know, at a frat party where all of the people eating the chicken salad were young and healthy, and then compare that to in a senior center, clearly there's going to be a higher attack rate. So those things, infectious dose and the immune status of the population you're talking about, are going to affect that attack rate. Okay, so there's two things, and it's kind of confusing. We need to talk about incidence and prevalence. And this guy does a good job. I'm going to go ahead and let it go to the end. I think at the end he gets a little, you know, a little too much. But the best one I could find, so we're going to just go with it.
Hey everyone, this video is about incidence and prevalence. It's absolutely crucial to understand what incidence and prevalence are and what the difference between the two is.
Incidence is a measure of disease risk, whereas prevalence measures disease burden. Incidence is defined as the number of new cases of a disease during a specific time period divided by the number of persons at risk for the disease during that same time period. The resulting proportion can be multiplied by 1,000 in order to get the number of new cases per 1,000 population, or by 100 in order to get the number of new cases per 100 population. That's up to the beholder. Let's take the example of a fictitious population of 10 women free from disease. 4 of these women develop uterine cancer during a given year. So the incidence is 4 divided by 10 times 1,000, equaling an incidence rate of 400 cases per 1,000 population per year. What's critical for incidence is that every person in the denominator must have the potential to become one of the people in the numerator. In fact, these 4 people are part of the denominator. They transitioned from disease-free to diseased. Incidence is a measure of events and therefore a measure of risk. So we said that everyone in the denominator must have the potential to become a member of the numerator or the diseased group. Let's come back to our study of uterine cancer. If 3 women of our fictitious population had their uteruses removed, if they had undergone hysterectomy, in other words, they would no longer have the potential to become part of the numerator. So instead of 4 divided by 10, it would now be 4 divided by 7 times 1,000 equals a new fictitious incidence rate of 570 per 1,000. Now what about prevalence? Prevalence is defined as the number of affected persons in the population divided by the number of all persons in that population at a specific point in time. So in this fictitious example, it would be 3 divided by 10 times 1,000, which would mean that we have a prevalence of 300 per 1,000 population. And what's the difference between incidence and prevalence? Let's take a group of 5 people who develop tuberculosis over a period of 6 months. 1 develops the disease in January, 2 in February, 1 in April, and 1 in May. So ignoring the denominator for now, the incident cases in February, for example, would be 2. Or in other words, 2 would be the numerator of the incidence rate for that month. And it would be 1 for the months of January, April, and May. Now, prevalence also takes into account the duration of the disease. Let's say case number 1 is cured in May, case number 2 is cured in April, case number 3 in March, case 4 and 5 during the second half of the year. Now let's look at the prevalence of tuberculosis in these months. Let's also just focus on the numerator or the prevalent cases during each month. We have 1 case in January, 3 cases in February, 3 in March, 3 in April, 3 in May, and 2 in June. So prevalence is determined by how many people join the prevalence pool or the incidence and how many leave the prevalence pool through death or cure. Let us depict that with a vessel full of pebbles. The vessel is filled with pebbles or new cases by the incidence rate, and it's emptied by death or cure. This means that if death goes up, then more people will leave the vessel, and if death goes down, then more people will stay in the vessel. And the same thing applies for cure. If more people are cured, more pebbles or people will leave the vessel, and if cure rate goes down, then more pebbles or people will stay in the vessel. Let's have a closer look. Let's say this is our baseline prevalence. Now, what happens to prevalence if incidence goes up while death and cure stay the same? It has to go up, right? What happens if incidence stays the same but death goes down while cure rate stays the same? It will go up since fewer pebbles will leave the vessel. What if death goes down and cure rate goes up? Well, as you probably guessed correctly, prevalence will decrease since more pebbles will leave the vessel. So prevalence is a measure of disease burden. As such, it is a great tool for planning the allocation of health services. So prevalence is incidence times duration. And duration is determined by the death rate or the cure rate. If the death rate or the cure rate go up, then the disease duration will be shortened. If death rate and cure rate go down, disease duration will be prolonged. At most points in time, prevalence will be lower with shorter duration and higher with longer duration of disease. Now let's use another fictitious example to clarify this point. Let's use an example of coronary heart disease in 2 different populations. One is the population of Hollywood. The other one is the population of the Bronx. Our fictitious Hollywood has a prevalence of 50 cases per 1,000 population. The Bronx, on the other hand, has a prevalence of 10 per 1,000. So, to the person who's not familiar with the fact that prevalence is not a measure of risk, but rather a measure of the burden of the disease, It looks like folks from Hollywood are at an increased risk of CHD, but that conclusion is not true at all here. Let's look at the incidence rates, duration of disease in both locations. Incidence is 5 per 1,000 per year in both locations, but duration of disease is 10 years in Hollywood due to better care, whereas in the Bronx, people die from CHD after 2 years. So, in fact, the higher prevalence in Hollywood is just an expression of better care of an incurable disease. You see, we said prevalence is equal to incidence times duration. So 5 times 10 is 50, and 5 times 2 is 10.
So I hope the difference between incidence and prevalence is now crystal clear.
So let's look at incidence. So incidence is the number of new cases of a disease in a population at risk during a specific time. So like I said, this is the risk of an individual contracting the disease. So yes, I pulled this off the internet again. So here are total number of new cases, and this is population for those different countries. And I'm just going to assume that everyone in the population is at risk. There's no way I can assess that. So we're just going to assume these are cases for COVID-19. So I don't know who has the antibodies or things like that. But we're just going to assume everyone is at risk. So that puts new cases per million, so the incidence, at 41 for the United States, 102 for Spain, and 35 for Italy. And like I said, if you were going to do it per 10,000, then you just do the math. You just move the decimal. So looking at this, what incidence does is it tells you the risk of someone contracting the disease. So you can look at this snapshot right now. In which country would you have a higher likelihood of contracting the disease COVID-19? So incidence assesses risk. So prevalence is the total number of cases of a disease in a given population at any time for a specific period in a given population. And so usually it's going to be, they'll assess these things in June, and they're sort of looking at it per year usually. But it reflects the overall burden of the disease on society because it takes into account the old cases that are still going on and the new cases. And so I think you did a great job showing you that is the longer the duration of the disease, the higher the prevalence. Because if the disease is ended by a quick cure or death, then that prevalence is going to be lower. So yeah, just showing this is incidence right here. Okay, so let's look at some other definitions. We have morbidity, mortality, and case fatality rate. So morbidity refers to illness. And so is the rate of illness of the disease in a population. So how many people per populace are sick from a particular disease. And so clearly if a disease is very contagious, then it's going to have a high morbidity in the populace. That's just because it can spread. Mortality refers to the overall death rate in a population. Like so many people per 10,000 die of this disease. When we talk about case fatality rate, that tells you the proportion of reported cases of a specific disease or condition which are fatal. And it's usually going to be in a specified time frame. So that indicates the severity of the disease. So Ebola, oops, my pointer's not working. So Ebola, 50% of the people that contract Ebola die. Spanish flu from the years of 1918 to 1919 was about 2% of the people that contracted Spanish flu died. So there was about 500 million that got the disease and about 50 million deaths. Influenza for any given year is going to be less than 1%. And so it just kind of gives you case fatality rate. You just take the number of people that have died from the disease and divide it by the number of people that had the disease. And that just kind of gives you the severity. Okay, so you've seen these definitions before. I just sort of added one of them. So remember we talked about endemic diseases. So these are diseases that are constantly present in the population. So you can just think of think of like there's always someone who has adenovirus, a lot of respiratory viruses, so common cold. So that's something that's always going to be around. So sporadic diseases, these are things that can just crop up from time to time. So I think every now and then tetanus pops up, or rabies, even the plague. Outbreaks, that is going to occur at a brief time in a specific place. And so we're going to watch the story of John Snow, and he looked at a particular cholera outbreak in 1854, Lyme disease, or a particular outbreak in 1975 in Old Lyme, Connecticut. That's how it got its name. So you can have outbreaks. Outbreaks, though, can spread, and so if they spread, then that becomes an epidemic. So then you have disease rates higher than usual. And also we know if there's epidemics and it spreads over several continents, then that becomes a pandemic. Just like the COVID-19 pandemic. So what we're looking at here, we've got percentage of deaths on this axis and then weeks of year. And so pneumonia, influenza, that's always going to be endemic. And so that's what that blue line is showing. And these are seasonal. Most of the time respiratory viruses are going to be transmitted in the winter months because people are indoors and they're closer together. So we've got this blue line, and then we have actual percentage of total deaths in population. You can see, when they go up above, this green line here is epidemic threshold. So it's just kind of showing you when it pops above there, like here it's quite high, and so it has exceeded the seasonal baseline, so then that would be in the epidemic range. So it's going to be above. So you can have things that are endemic, constantly present, that can, if they're higher in numbers than usual, then it becomes an epidemic. So we've seen this before, so we're just going to kind of go over the chain of infection again. The spread of infectious disease follows these series of steps, and knowing the chain for any given disease allows for determination of any place that that chain can be broken. All right, so reservoirs. So reservoirs of infection are going to be the natural habitat of a pathogen. So this is going to be the source of that pathogen. And so what the reservoir is going to sort of affect the extent and distribution of the disease. And so we're going to look at different human reservoirs, obviously when someone's sick or if someone is a carrier. When we talk about non-human sources or reservoirs, if it's an animal, whether it's a domestic animal or a wild animal or the environment, these are obviously going to be harder to control. And these are going to be diseases that we are not going to be able to eradicate, because to do that, you have to kill that whole population of animals. And I don't know, people kind of frown at that. And then we're not really going to be able to get rid of things in the soil or naturally occurring in water. Okay, so let's look at some human reservoirs. So let's look at a symptomatic infection. We know that there is an incubation period. That's the time between the exposure to the onset of illness. So someone can be infectious during this time. We know that when they're experiencing those signs and symptoms of the disease, hopefully they stay home, but they can also be capable of spreading that infection. And then sometimes too, even after those symptoms go away, with some diseases, people can still be infectious. So you kind of know, though, if someone's having symptoms, but if someone is asymptomatic, it's going to be harder to identify. We talked about carriers. So there's carriers to certain diseases. In populace, we have a high carrier rate for Streptococcus pneumoniae, Mycoplasma pneumoniae, and so it can be spread to others. We also talked about hepatitis B being a chronic infection. So two, though, someone can be exposed. So they're exposed, but their immune system is responding. So their immune system is responding, it's fighting that pathogen, but they are unaware. And so we talked about Neisseria gonorrhea, and also a lot of other STI, sexually transmitted diseases for women, are usually asymptomatic. And so a woman doesn't know she has these diseases and can spread it to her sexual partner. We also talked about Salmonella typhi. We talked about Typhoid Mary. So that was the Irish cook. She harbored the Salmonella typhi in her gallbladder. And so she was not washing her hands. And so she was getting a lot of people sick with typhoid. And a lot of those people were dying. Sometimes it's just part of their normal microbiota. And so many people carry Staphylococcus aureus on their skin and in their nostrils, so it's pretty high. We'll talk about it again when we get to hospital-acquired infections. But basically, humans being reservoir of disease and then passing it on to someone else, so communicable diseases. So non-human reservoirs, when we're talking about animals, obviously they're going to be difficult to control in the wild. And so we talked about plague, so rodents and their fleas, so prairie dogs and other mammals, rabies, raccoons, skunks, bats, Campylobacter, salmonella, they're going to be in poultry. So anytime there is an animal population that serves as a reservoir, bats per se for coronavirus, really difficult to control these diseases. Just definition of zoonoses, these are diseases that exist mostly in animals, and the animals really aren't sick from them. But then when they jump species and they're transmitted to humans, usually they're be more severe in humans because there's no evolution towards balanced pathogenicity. And so what that means is if you're going to be a good pathogen, it's a really good idea if you do not kill your host. And so if it is an animal disease, it has evolved to be sort of tolerated by the animal, so that animal can continue to be the host and can continue to spread it in the populace. And so that's why a lot of these zoonotic diseases are way more severe in humans. And so 75% of emerging diseases come from an animal origin. So when we talk about environmental reservoirs, yeah, difficult to impossible to eliminate. So think about soil and water. So all the Clostridiums, so Clostridium tetani, Clostridium botulinum, Clostridium perfringens, those are all soil-borne. They also spore formers. You are not getting rid of those. Think about those fungal infections we talked about, histoplasmosis, coccidioidomycosis, which is that valley fever. Yeah, those were all from inhalation of fungal spores. So growing either in the dirt, we talked about histoplasmosis, that was on, bat dung in caves. But either way, you can't really control those environments. You can try to stay away from them and try to do that, but you're never going to get rid of those diseases. All right, so portals of exit. So a portal of exit is the route by which an infectious agent leaves its host. And so think about the intestinal tract. So a lot of those gastrointestinal diseases, your book just gives Vibrio cholera, sure, we'll go with that. They're going to be shed in feces. Respiratory tract, usually they're going to leave through saliva, mucus, those droplets whenever someone sneezes or coughs or talks. Skin, anything on the skin can be shed on the skin cells like Staphylococcus aureus. And of course, those genital pathogens, they can exit through basically secretions, so either semen or vaginal secretions, so STDs like Neisseria gonorrhea. So those portals of exit, usually the disease is going to sort of help that pathogen leave. So if it's anything respiratory, someone's going to get caught, they're going to cough, they're going to sneeze. And if it's something through the gastrointestinal tract, it's probably going to cause diarrhea. So that pathogen can exit. So disease transmission, there's vertical transmission and horizontal transmission. And so when we talk about that vertical transmission, it's going to be from mother to child. And so a pregnant woman to a fetus, there are some diseases that cross the placenta. So syphilis, so we talked about congenital syphilis, toxoplasmosis, that was a protist. If a woman has not been exposed to toxoplasmosis before, she should avoid cleaning the cat box. Listeriosis, rubella, German measles. We really didn't talk about that one. It is covered by vaccines, so it really isn't very prevalent, but it's not one we want to drop and lose that herd immunity because it can cause miscarriages. Also, HIV, the virus that causes AIDS, can cross the placenta. During childbirth, so exiting out that vaginal canal, so most of those STIs are gonorrhea, chlamydia, herpes, and HIV. There's not very many that a mother can transmit to her baby through breastfeeding, but contraindications are for HIV and Ebola, meaning if someone is HIV positive or has Ebola, they should not breastfeed their child. So disease transmission can either be direct or indirect. So if it's direct, it involves immediate transfer of infectious agents to that portal of entry. So we talked about touch. So touch can be anything from a handshake to sexual intercourse. This is going to be easiest, of course, when the infectious dose is low. Hand washing is considered the single most important measure for preventing the spread of infectious disease. There are some pathogens that can only be spread through really intimate contact. Too, especially so Treponema pallidum that causes syphilis, Neisseria gonorrhea causes gonorrhea. They can't handle cool temperatures or desiccation, so drying out. So it has to be transmitted through that intimate contact. Oh, let's talk droplets, shall we? We've been hearing a lot about that on the news lately. So droplet transmission. So it can spread respiratory disease. Those pathogen-laden droplets are then going to be inhaled. So we talk about there's a difference between droplet and droplet nuclei transmission. So we hear about droplets. These are what are considered big droplets, so bigger than 5 to 10 micrometers. These are the ones that are generally going to fall to the ground within a meter, so that's about 3 feet. Spread is minimized by covering your mouth when sneezing. I have some stats for you, because yeah, you wanted to know. So when someone sneezes, they say that there is about 40,000 droplets that leave, and they are leaving at a speed of 223 miles per hour. So yeah, so please, proper sneezing etiquette. It's best to just sneeze into the crook of your arm. When someone coughs, it is estimated that about 3,000 droplets leave. These are larger droplets too, so if they are inhaled, usually they are going to infect the upper respiratory tract. So indirect transmission, which means without contact. So basically through the environment, the air, contaminated food, water, or inanimate objects. So now we're still talking about airborne. So respiratory diseases are often transmitted by what are called droplet nuclei. So these are more the smaller ones. If you're really not, actively spraying, there still are tiny little aerosols. So these are going to be small droplets, so less than 5 micrometers. And two, what can happen is in these droplets can attach a dry material like dust or whatever. They dry, they stay attached, and the book and other people say that basically these little tiny droplets can just drift on air currents basically indefinitely. So things like whooping cough, Neisseria meningitidis, those are highly contagious because that droplet nuclei, they can just hang out in the air on these aerosols. And two, since these are small little droplets, when they're inhaled, they can actually go to the airways into the lungs. Other airborne particles, yes, when you breathe in, you're probably breathing in someone's dead skin cells. You breathe in dust, which could also have microbes attached to it. Of course, if anytime people are in dense populations like crowds, that's going to increase the number of bacteria that are floating on these little aerosols, these little droplet nuclei. Still, so it's very difficult to control these, and we talk about hospital-acquired infections, I'll bring it up again. So having proper ventilation systems, and in one way that they can do that is through negative pressure. So airflow always moves positive pressure to negative pressure, and so by creating negative pressure zones in a hospital or in a building, then that can sort of move air from one place to another. So like out of an OR into a hallway, or out of a patient's room into a hallway. And then two, those HEPA filters, so those high particulate air filters, they can help remove those particles from the air. So they can be airborne or they can be vehicle-borne. So that means transmitted by objects. So objects can be food or water. So we're talking about inanimate objects, so meaning not food and water. They're called fomites. So just our clothing, keyboard, your phone, doorknobs, anything someone touches, that's considered a fomite. Food and water can also become contaminated. And so we know animal products, particularly meat and eggs, from the animal intestines, that bacteria can be on those products. So like Salmonella, Campylobacter, Two, that cross-contamination. So this picture right here is really poor practice to cut raw meat on the same cutting board that you're going to cut your vegetables. And so that's how a lot of that transfer can occur. We also know sometimes that municipal water systems can also become contaminated. We learned about crypto. So Cryptosporidium parvum is really difficult to treat. That can stand some chlorine, and so that they had an outbreak in Wisconsin in 1993. So just vehicle-borne would be fomites, inanimate objects, or food and water. Can also be vector-borne, and so we've talked about vectors before. It's a living organism that can carry a pathogen. We never really distinguish between the two. So a mechanical vector is going to be something that carries microbes on its body from one location to another. So flies are pretty gross. They love feces, and then they can just pick up some Shigella, which has a low infectious dose of about 10, and land on some meat, like at a picnic or something, and then it gets ingested. Biological vectors, those are the ones we talked about that participate in the life cycle of the pathogens. So mosquitoes and malaria. We talked about the tsetse fly for trypanosoma and African sleeping sickness. So ticks for Lyme disease. And so if you know what the biological vector is, often if you control that vector, then you can prevent that disease. And so if you remember the virtual lab, how the U.S. used DET to basically, as an insecticide, did not do very nice things for our bald eagles, but it did wipe out mosquitoes, and so that sort of helped remove malaria. We still have about 1,500 cases of malaria a year, but for the most part, we don't have to worry about it. And usually those cases of malaria come from someone who's visited another country. All right, so we've done reservoirs, we talked about portal of exit, types of transmission, and then that portal of entry. And so it's really going to be through skin or those mucous membranes. And of course, we talked about portal of entry is going to be specific for a particular type of disease. Our skin, when it's intact, that first line of defense is really difficult to penetrate. So usually this is going to be through a wound or bite from a vector. Mucosa, portal of entry is going to be the most common. So respiratory is going to enter through like those droplets. So it's going to be inhaled. Something that's going to attack, or the digestive system is going to be ingested. And then something that's going to affect the mucosa, the genital urinary tract, is going to be introduced through sex. Also, eyes is also another portal of entry I didn't put on there. Okay, I think I'm going to stop right here. I hope you have an awesome day, and then we will finish up epidemiology in part 2.